Hello. So, we in this lecture as well, we will continue to talk about approximate method, which will include Rayleigh-Ridge method. So, in the last lecture, we have started talking about the Rayleigh-Ridge method. We discussed what is meant by Rayleigh's quotient and how can we find out the natural frequency of a system using Rayleigh's quotient. So, here we were trying to find out that what would be the Rayleigh's quotient for a continuous system and how this Rayleigh's quotient can be used for in form of Rayleigh-Ridge method to obtain the natural frequency and mode shape of beams and bars with complicated geometry. Let us move on to the derivation. So, in the last class we have seen that the Rayleigh's quotient Ru, which can also be written as omega r square, for a rod under for a bar under axial vibration can be written as 0 to L E a x, which is a function of x, then phi dash x and square of that into dx by where phi x is the mode shape of the system and omega r will be the natural frequency corresponding to that mode shape of the system. Now, we said that how are we going to use it? We are going to assume a solution for the mode shape, an approximate solution for the mode shape or a trial mode shape, and see for what trial mode shape the Rayleigh's quotient is minimum, and that minimum value corresponds to the natural frequency of the system, and that trial mode shape which is giving me the minimum value of the Rayleigh's quotient correspond to the best approximated value of the mode shape. So, now what we do in Rayleigh-Ridge method is a much more formal way of solving it. So, in Rayleigh-Ridge method we try to obtain a trial value of the mode shape phi x, and we see for what trial values of phi x the Rayleigh's quotient is minimum. So, how do we do it? We do it by saying that the mode shape is nothing but summation of certain constant psi I into certain trial function psi I x, I equals to 1 to n. So, where C I are constants, are unknown constants. And psi I x, which is a function of x, are called the trial function. Trial functions. So, what are these trial functions? The trial functions are certain known functions. This trial function can be anything. It can be a trigonometric function, it could be a polynomial function, but a known function. And the only criteria on trial function is that the trial function should satisfy the boundary conditions on displacement slope, etc. And it need not satisfy the natural boundary condition which are the boundary conditions on or boundary conditions on force, moment, etc. Okay. So, let me just summarize this once more. So, what are we going to do? We are going to assume a value or we are going to assume an approximate mode shape. How are we going to do that? We are going to write the approximate mode shape as a summation of several trial functions. These trial functions are known functions. For Rayleigh-Ridge method, the trial functions need to satisfy the boundary conditions on displacement, slope, etc., and need not satisfy the boundary condition on shear force, moment, axial force, etc. So, these known trial functions are then used to get an approximate mode shape by writing that in a summation form. So, I will take say 5 trial function, then my approximated mode shape is C1 into psi 1 x plus C2 into psi 2 x plus C3 into psi 3 x plus C4 into psi 4 x plus C5 into psi 5 x. This is what we are going to do. The number, so this number n denotes how many trial functions are we using. It is needless to say, it is very intuitive to understand that the more the number of n, the better approximation we are going to achieve. But then by increasing n, we also increase the computational requirement of the process. So, we always try to optimize n. We always try to take minimum number of n to get the best value of the approximated mode shape. This can be done by choosing a trial function which would be a good approximation of the possible mode shape of the structure. Now, let us go ahead further and see how we can get this in a more detailed form. So, therefore, Rayleigh's quotient omega r square is nothing but 0 to L E A x. Now, I had phi dash x. So, I have phi dash x whole square into dx. Now, what into dx. Now, what am I going to do? In place of phi dash x, I am going to put the summation C I into psi I dash x. So, if I do so, then this also is going to become 0 to L m x into C I psi I x whole square dx, and this also is going to become summation of C I psi I dash x whole square. So, let me just write this as n by t, where n is the term corresponding to the numerator and d is the term corresponding to the denominator. Now, C1 are unknown, Ci's are unknown. So, how am I going to find out Ci? So, now what I say, the best approximation for the mode shape is going to be obtained when that approximated mode shape is minimizing the Rayleigh's quotient. That is the Rayleigh's theory, right. So, I have to find out Ci such that those Ci's are going to minimize the Rayleigh's quotient. So, how am I going to write this mathematically? I am going to write this as R del R u by del C j, which is going to be del omega r square by del C j, and that is going to be del C j by of n by d, and that should be equal to 0. So, if Cj is making Rayleigh's quotient minimum, then del Ru by del C0 Cj has to be equal to 0. Now, what is del by del Cj of n by d? So, that can actually be written as, this whole thing can be written as d into del n by del Cj minus n by del d by del Cj by d square should be equal to 0. So, this whole thing can be implied at written as d by del n by del Cj minus n del d by del Cj is equal to 0. So, that is going to imply as del n by del Cj minus n by d into del d by del Cj is equal to 0. Now, n by d is omega r square. So, therefore, this equation can be written as del n by del Cj minus omega r square by del d by del Cj is equal to 0. So, if I can solve this equation, I should be able to get hold of Cj. Now, how am I going to do that? So, let me just rewrite this. So, I will have del n by del Cj minus omega r square okay. So, del n by del Cj, what is that? So, that is del by del Cj of this integral 0 to L E A x summation of C I psi I dash x whole square dx. Now, if I take the derivative, then I will get this as 0 to L E A x summation of C I psi I dash x by psi j dash x into dx. This is what I am going to get. So, now I have to write this whole thing for j equals to 1, 2 and so on till n. Now, so if I expand this expression, what am I going to get? I am going to get E A x C1 psi 1 dash x into psi dash j x plus So, this can be written in a very summarized form as C1 into k j1 plus C2 into k j2 plus so on up to Cn into k jn, where k j1 is this term, k j1 is this term, and so in a generic form I can say that k j I is going to be EAX psi I dash x psi j dash x. And another thing that should be noticed is that k j I is always going to be k I j. So, this whole expression has been written for some generic j. Now, if I write this expression for all possible values of j from 1 to n, I can actually write this expression in a matrix form, which will be a K matrix into C1, C2 and so on till Cn. Therefore, the first part of this expression can actually be written as a matrix, which I am calling K into C1, C2, C3, Cn. Now, let us see what should we do next. So, then let us see what is del d by del Cj. Del d by del Cj is del by del Cj into 0 to L. So, there was a mistake in the last slide. K I j terms had this integral, which I kind of missed writing. So, it is summation of C I psi I x whole square dx. So, if I do the differentiation, I am going to get 0 to L mx psi I So, if I expand this, this is going to be 0 to L mx C1 psi 1 x psi j x plus 0 to L mx C2 psi 2 x psi j x dx and so on till 0 to L mx Cn psi n x into psi j x into dx. So, this can further be written as C1 into m j1 plus C2 into m j2 plus so on plus Cn m j n, where m I j is the integral of 0 to L mx psi I x psi j x into dx, and that is equal to m j I. So, if this is for a particular j, and if I write it down for j equals to 1, 2 till n, then this again can be written in a matrix form m, which is n cross n, and into C1, C2, C3, so on till Cn, and this is what we get. Now, then if I summarize this whole thing, then n del n by del Cj minus omega r square del d by del Cj can be written as the K matrix into C1, C2, Cn minus omega r square into the M matrix into C1, C2, Cn, and that is equal to 0. So, the element of Kij element is nothing but 0 to L Eax into psi I dash x psi j dash x into dx, and similarly Mij is 0 to L mx psi I x now. This equation can therefore be written in a condensed form as K minus omega r square n into C is equal to 0. So, this kind of expression we have solved earlier. So, this expression, so I know K, I know M, I do not know omega r square and I do not know C. So, these two are unknown. So, but I can solve this equation, I have solved similar equation, and that will give me the value of omega 1 square, omega 2 square and till omega n square, and corresponding to each omega I am going to get a C1, I am going to get C2 and so on, I am going to get Cn. Now, once so this omega 1 omega n square, this are the, so this are the approximated value of the approximate value of square of natural frequency. And this, once I know C1, C2, C3, I can always say that the approximate value of phi1 is going to be Ci psi I x. So, psi I is known, this is going to be known from here. So, I can also get the approximate mode shape. And this is how we can use Rayleigh-Ridge method to obtain an approximate value of the natural frequency and the mode shapes. Now, we can see that if we have used n trial function, we will get n natural frequencies and the corresponding n approximated mode shape. Now, we can also see that the accuracy of this approximate natural frequency and mode shape depends on the number of trial function we use, 1, and 2, the nature of the trial function. If the trial functions are very similar to the mode shape of actual mode shape of the system, then of course, we are going to achieve better accuracy. So, with this we are going to solve an example problem and thereby end the lecture. So, let me get into the example problem. So, we have this example where we have a So, we have a bar, a fixed free bar under axial vibration. So, it is undergoing a displacement which is u x comma t, but it has a linearly varying cross section such that E A x is going to be 2 E A 1 minus x by L. So, at x equal to 0 it is 2 E A, and at x equal to L it is 0, and similarly the mass distribution is also given as 2 m 1 minus x by L, where E A and m are known. Now, how are we going to find out the natural frequencies and mode shapes using Rayleigh-Ridge method? And it has been said that we can use only 2 trial functions. This is the requirement of the problem, but we are free to choose any number of trial function. The more the trial function, the better the solution, as well as the more the trial function, the more computationally difficult it becomes. So, now let us see how are we going to solve the problem. Now, let us see what is going to be the trial function. So, let us assume the trial function. So, let the trial function psi 1 x be equal to sin pi x by 2 L, and let psi 2 x be equal to sin 3 pi x by 2 L. Now, you can see that sin pi x by 2 L, which is my first trial function, is an acceptable function, because at x equal to 0, psi 1 x is equal to 0, or it is satisfying the fixed boundary condition where displacement is equal to 0. Similarly, psi 2 x is also a 0 at x equal to 0, therefore, it is also satisfying the fixed boundary condition. So, psi 1 0 is equal to 0. So, this is satisfying displacement equal to 0 at fixed end, right, and this psi 2 0 is also equal to 0, which is also satisfying displacement equal to 0 at fixed end. So, these two are acceptable function. So, therefore, my trial functions being this, my approximated mode shape phi 1 x is going to be C 1 psi 1 x plus C 2 psi 2 x. So, this is going to be my approximated mode shape. So, let me say that this is and C 1 and C 2 are unknown constants which we need to find out. How are we going to find out? So, I will skip the derivation we have already done. So, the final expression that I am going to get is k 1 1, k 1 2, k 2 1 and k 2 2 in minus omega square r square into m 1 1, m 1 2, m 2 1, m 2 2 into C 1 and C 2 has to be equal to 0. Now, I know that k I j, which is equal to k j I, is 0 to L E A x into psi 1 dash x, psi I dash x, psi j dash x into dx. Therefore, K11 is going to be 0 to L, EAX is 2EA and what psi 1 dash x whole square into dx, which is going to be 0 to L 2EA. So, psi 1 dash x, psi 1 x is pi x by 2L. So, psi 1 dash x is going to be pi square by 4L square into sine square pi x by 2L into dx, which is going to turn out to be EAL. If you evaluate this integral, you will see that this integral is equal to EA by 2L 1 plus pi square by 4. Similarly, K12 is going to be K21 and that is going to be 0 to L 2EA and that if you evaluate, it is going to be 3EA by 2L. Similarly, I can find out K22, which is going to be, so K22 is going to be 0 to L psi 2 dash is going to be 3 pi by, so 9 pi square by 4L square into sine into cos, into cos 3 pi by 2L x whole square into dx, and that is going to be 1 plus 9 pi square by 4 into. So, my K matrix, which is 2 cross 2, is going to become EA by 2L into 1 plus pi square by 4 plus 3 and then 3 and 1 plus 9 pi square by 4. So, this is my K matrix. So, what is my Mij? Mij term is 0 to L mx psi I x psi j x into dx. Therefore, M11 is 0 to L 2m 1 minus x by L into sine pi x by 2L to sine 3 pi x by 2L dx, which is going to be mL by 2 into 1 minus 4 by pi square. Similarly, M12 is going to be M21, which is going to be 0 to L to M. Sorry, I made a mistake here. So, this is going to be sin pi 2 M (1 minus x by L) into sin pi x by 2L sin 3 pi x by 2L into dx, and that we can evaluate, that is ml by 2 4 by pi square. Similarly, M22 I can derive, and M22 is going to be 1 minus 4 by 9 pi square into ml by 2. So, therefore, I can get my M matrix as ml by 2 1 minus 4 by pi square 4 by pi square So, I have now go back to the previous equation, minus omega square m into C1 C2 equals to 0. So, out of this I know this, I know this, I can solve for this and I can solve for this, and this is going to give me the two values of, so this is going to give me omega 1 square and omega 2 square, and this is going to give me C1 C2 1 and C1 C2 2, and this is further going to give me phi 1 x, this is going to give me phi 2 x, and this is how I get the approximated value of mode shape and the natural frequency using Rayleigh-Ridge method. So, this was for a bar undergoing axial vibration. Now, if we quickly look into what would be the Rayleigh's quotient for a Euler-Bernoulli beam, then you can find out the energy, kinetic energy and the potential energy, and you will see this would be nothing but phi double dash x whole square dx by 0 to L mx into phi x whole square dx. So, this is Rayleigh's quotient for Euler-Bernoulli beam. So, you can always find out the expression of strain energy and the expression for kinetic energy for an Euler-Bernoulli beam, and you will see that the Rayleigh's quotient for Euler-Bernoulli beam is going to be of this form, and we can use the same method that we have used for the previous example of a bar, and then we can again from this we can get the same equation of k minus omega square m into C1 C2 or C till n C n is equal to 0. So, which is going to be very straightforward. So, with this we are going to end today's lecture. In the next lecture, I will talk about another approximation method which is called the collocation method. The collocation method will also be used to solve the mode shape and natural frequency of a beam and a bar having complex geometry. Thank you.